All right, let's talk about one of the most fundamental processes in all of manufacturing, metal casting. We're talking about turning scorching hot molten metal into the solid, essential parts that really build our entire world. It sounds straightforward, but it's actually this high-stakes dance with the laws of physics.
I mean, think about it. You pour liquid metal into a mold, you wait for it to cool down and solidify, and bam, you've got your part. Simple, right? But in that critical moment, that transition from a liquid to a solid, well, that's where the drama happens.
And a whole lot can go wrong, as it turns out. Just look at this thing. This defect is called a mismatch, and it's exactly what it sounds like. It happens when the top half of the mold, the cope, and the bottom half, the drag, aren't lined up perfectly. It's a perfect example of how one tiny process error can make the final part completely useless.
So let's put a formal name on it. A casting defect is basically any unwanted glitch or irregularity in a metal casting. And this isn't just about looks. A single defect can create a hidden weak point, and that can lead to a catastrophic failure in a really critical component. So yeah, understanding these flaws is absolutely vital for cost, for safety, and for performance.
Okay, let's dive into the specifics. As you can see here, there are a ton of ways a casting can go wrong. It might look a little overwhelming, but the good news is they all fall into just a few main families. So we're going to break them down and make this whole thing a lot easier to wrap your head around. First up, defects caused by trapped gas. This is all about what happens when gases, whether from the air, from moisture, or even from the metal itself, form little bubbles that get stuck as the metal hardens around them. And this slide shows you exactly what that looks like. On the left, you've got a diagram of a sand blow, and on the right, a real-life blowhole. It's literally a hollow cavity, kind of like a fossilized bubble, and it creates a massive weak spot right inside the casting. Not good. So you have to ask, right? Where does all this gas even come from? And why on earth does it get trapped inside solid metal? Well, the key thing to remember is that gas needs a way to escape. The usual suspects are things like too much moisture in the sand that instantly turns to steam, or sand that's packed so tightly, what we call low permeability, that the gas just can't push its way out. The solutions then are all about giving that gas an escape route, like properly baking the cores to get all the moisture out and adding vents to the mold. Okay, now for our next category. These defects come from a basic, unavoidable law of physics. Almost all metals shrink as they cool down and turn solid. You can't stop it from happening, so you have to learn how to manage it. And when that shrinkage isn't managed correctly, you get this, a shrinkage cavity. It's a void that forms because there just wasn't enough liquid metal left to fill in the space as the part solidified. And as you can see, these things can be on the surface, or even more dangerously, they can be hidden deep inside the part. But hold on, why does this even happen? If the entire part is shrinking, why does it create one big void instead of just, getting a little bit smaller all over? The secret is in the cooling process. Different sections of the casting solidify at different speeds. If one area gets cut off from the supply of fresh, molten metal too soon, it basically starves and a void opens up. The clever solution is something called directional solidification. This is where you design the mold with extra reservoirs of metal called risers. You design it so the main part solidifies first, and that disposable riser solidifies last, trapping the ugly shrinkage cavity in a piece you were just going to throw away anyway. Now, a nasty cousin to shrinkage cavities is something called a hot tear. And what's so wild about these is that the casting is literally tearing itself apart. As it shrinks, if the mold or the core inside it doesn't give way, or if the design has a lot of sharp corners, incredible stress can build up while the metal is still hot and weak. The result? These jagged, ugly cracks. All right, our third category shifts the blame a little, removing away from the metal's own properties and looking at the external stuff, the mold itself, and the way we pour the metal into it. On the left, we've got a misrun. This is where the metal just didn't have enough heat or flow to fill up the entire mold before it started to solidify. Then on the right, you see a cold shut. This is what happens when two streams of molten metal meet, but they're just a little too cool to fuse together properly. It creates this weak seam that looks just like a crack. So, what in the world could stop a giant flood of superheated liquid metal from filling up a simple little cavity in a mold? It almost always comes down to two things, flow and temperature. The main problem is usually metal that's poured too cold or a part design with sections that are just too thin to fill. The solution is finding that golden window for your temperature. Hot enough to flow, but not so hot it causes other problems. It also means you need a really efficient gating system. Those are the channels that guide the metal, and, of course, clamping that mold down tight to avoid the mismatch we saw at the very beginning. So, we've looked at a bunch of specific defects. Now let's zoom out and look at the big picture. How do we go from just fixing problems to actually preventing them from ever happening in the first place? Here it is, the main takeaway. Whether you're talking about a gas bubble, a shrinkage cavity, or a misrun, pretty much every single defect comes from a failure to control the fundamentals. These are the 4 pillars of good casting: temperature, your materials, the mold design, and time. We can really boil all this down into 3 core principles. First, control your inputs. Use clean metal, use well-prepared stand. Second, optimize your design. Your mold and gating system have to be intelligently designed to guide that metal exactly where it needs to go. And third, you have to manage the cooling process. That's the most critical stage, where you use all those design tricks to control how the casting solidifies. Which kind of brings us to a final thought. A perfect, flawless casting, it's really more than just a hunk of metal, isn't it? It represents a victory of human engineering and precise control over some of the most powerful and, frankly, unpredictable forces in physics. Thanks for watching.